everyone, welcome to the lecture series of Applied Physics. This is Fiber Optics Part 1 by Dr. S. Deepthi, Assistant Professor in Physics, Department of H&S, MLR Institute of Technology, Hyderabad. Now we are going to discuss about fiber optics. Okay, this is the overview. That is, we are going to discuss about what do you mean by fiber optics here in this one, and next we shall discuss about the structure of an optical fiber, the principle of optical fiber, that is the total internal reflection, acceptance angle and numerical aperture in this video lecture. So, fiber optics. Fiber optics means it is a branch of physics which deals with the transmission and reception of light through optical fiber. We will see many optical fibers in our daily life. That means in an optical fiber means the name itself suggests that whenever the light transmits through a small region, through a small aperture, which is known as optical fiber. So the transmission of light through this one gives us the optical fiber, complete optical fiber. So the optical fiber is a cylindrical waveguide. This is the representation of a cylindrical waveguide, and which is operated at optical frequencies. Optical frequencies means the light going frequencies, the light transmission through one end to another end. That is, the optical signals can be transmitted through the fiber over long distances. This is the definition of optical fiber. See the figures over here. This is the representation of a first one is the representation of a bunch of optical fibers. Okay, the bunch of optical fibers where the light is being transmitted through each and every optical fiber. And here the whole world, the second picture depicts that the whole world is going with the optical fiber system itself. Next, this is also representation of an optical fiber where we can see the light is being transmitted through the cables. Now, what is an optical fiber? Let us go with the structure of an optical fiber. The structure of an optical fiber consists of 5 major parts. Okay, an optical fiber is a flexible, thin, transparent plastic or glass in which light is transmitted by a multiple total internal reflections, where this is the principle of an optical fiber we shall learn afterwards. Okay, this is a flexible, thin, transparent plastic. Flexible means even if it is if we do like this also, then it will open in a wider range. Okay, that is the flexibility. Okay, so it consists of core, cladding, buffer coating, strength members and protective jacket. So these are the 5 parts. Okay, so it is made up of transparent, dielectrics, glass or plastic. For example, this is a silicon dioxide is the example. An optical fiber consists of central core, glass, 550 micrometers diameter, 50 micrometers diameter. Micro means 10 to the power of minus 6 meters. That means it is very thin. It is as thick as our hair. Okay. So an optical fiber consists of central core glass. This is the center one. So as we know, we have seen in this diagram, there are a bunch of optical fibers, and we are now dealing with the single optical fiber. So the single optical fiber consists of this much. Okay. And cladding of diameter 120 to 200 micrometers diameter. That is, the refractive index of a core is greater than cladding, and the refractive index of core will be greater than cladding. The cladding is enclosed by string members called Kevlar and polyethylene jacket, which acts as a protective skin for core and cladding. So the light is being transmitted between core and cladding, and these acts as buffer coating, strength members and protective jacket will protect the entire system. Okay. The protective layer is used so as to make the optical fiber to withstand hard pulling, bending and rolling, etc. So this is about the structure of an optical fiber. Now coming to the principle of an optical fiber, as we have already learned about total internal reflection, let us recall about total internal reflection. So the principle of optical fiber is total internal reflection. Okay, if we observe the diagrams over here, whenever the light enters from a denser medium to a rarer medium. So the light enters from a denser medium to a rarer medium, it bends away from the normal. What it will do? It bends away from the normal. Okay. So whenever the light enters from a denser medium to a rarer medium, it always bends away from the normal. At a particular angle of incidence, the light just passes through the surface of separation of two media. So this is known as critical angle. Okay, the light just passes through the surface of separation of media. This is known as critical angle. And at a particular angle of incidence, even if the angle of incidence is increased, then at a particular angle of incidence, the ray of light just bounces back into the same medium. This is known as the bouncing back of light into the same medium after refraction is known as total internal reflection. That means when in which medium the light starts our incidence, then the light bounces into the same medium. This is known as total internal reflection, which is the principle of optical fiber. Here, the refractive index of core is greater than cladding, so that the light enters from core and cladding interface will undergo total internal reflection within the optical fiber. So, Snell's law gives us the relationship between angle of incidence, refraction and refractive indices of the two medium. N1 sin theta 1 is equals to N2 sin theta 2. Okay, this is the representation of a Snell's law. If the optical fiber, the core is a denser medium and the cladding is a rarer medium, as we have already known. When the ray of light enters from core cladding interface, it undergoes through total internal reflection. See, this is the representation of a total internal reflection through optical fiber. The representation here, see the diagram over here. Whenever the light enters to the core cladding interface, since N1 is greater than N2, the ray of light will be undergoing through total internal reflection and it will go like this. The transmission of light will be in this form. Okay. Next, acceptance angle and acceptance cone. What do you mean by acceptance angle? The acceptance angle may be defined as maximum angle of incidence that the light ray makes with the axis of the fiber to get the total internal reflection. Okay. In order to get the total internal reflection, the light should be incident at a particular angle of incidence such that the total internal reflection to be take place. Okay, so the light rays contained within the core having a full angle 2 theta A are accepted and transmitted along the fiber. Therefore, the cone is called as acceptance cone. So, this is the core cladding interface. Once again, we shall represent over here. Okay, so this is the core and here okay, so whenever the light enters at a particular angle of incidence, okay, and that angle of incidence is known as theta A and the light enters from both the sides. So this is also theta A. So the total thing becomes either 2 theta A, which is known as acceptance cone. This is the cone formation and where the light enters through core cladding interface in the both directions and will get the final output. Okay, this is the data transmission of data through the optical fiber. Okay, so here N1 sin theta C, where N1 sin theta 1 is equals to N2 sin theta 2, which is the Snell's law. Theta 2 is equals to 90 degrees. Theta 2 is equals to 90 degrees, then only the total internal reflection occurs. So N1 sin theta C is equals to N2 sin theta 90. So sin theta C is equals to N2 by N1 and theta C is equals to sin inverse N2 by N1. Okay, so this is the representation of the critical angle. Sin theta C is equals to N2 by theta C is equals to sin inverse N2 by N1. Now, we are going to calculate acceptance angle by using the formula sin theta I max is equals to sin theta I max means sine theta A, okay, is equals to N1 by N0 or Ni by 0 root over N1 square minus N2 square by N1. Okay, so N0 is the refractive index of air. Okay, refractive index of air. And so sine theta A is equals to, here we'll write here, sine theta A is equals to N1 square minus N2 square under root. This is the representation of a sine theta A, which is known as acceptance angle. Next, numerical aperture. Numerical aperture is defined as light gathering capacity of an optical fiber and is proportional to the acceptance angle. Okay, so we'll always calculate the numerical aperture in order to know the capacity of an optical fiber. Sometimes it is called as a figure of merit of optical fiber. It is a measure of amount of light that can be accepted by the fiber. This is known as numerical aperture. Numerically, it is equals to the sine of acceptance angle. Since it is known that numerical aperture is directly proportional to the acceptance angle, so numerically it is equals to sine theta A. That is equals to N1 square minus N2 square under root by N0. If N0 is equals to, if air is the medium, then N0 is equals to 0. Then N1 is equals, Na is equals to root over N1 square minus N2 square. Now, let us do the small calculations in order to get the fractional difference between refractive indices of core and cladding. So, there will be a small difference between the refractive indices of core and cladding. If the refractive index of core will be 1.46, the refractive index of cladding will be, it should be greater than. So, if the refractive index is 1.466, let us suppose the refractive index of core is equals to 1.466 N1, then the refractive index of cladding will be 1.46 N2. There will be a small difference between the refractive indices of core and cladding. Why? Because the core is having smaller diameter and also the cladding is having very smaller diameter. So, the light entered will be very minute, but the light entered will have some difference between the refractive indices. Okay, Na is equals to, let us do some calculations. N1 square minus N2 square can be written in the formula A plus B into A minus B. So, N1 plus N2 into N1 minus N2. N1 plus N2 can be taken as 2N1 and let us consider as N1 minus N2 itself. So, 2N1 square by, it is written as just multiplying and dividing with N1. N1 minus N2 by N1, that is equals to N1. Let us keep the N1 outside. 2 into N1 minus N2 by N1. So, this is taken as delta, which is the fractional change. Delta is equals to 2 into N1 minus N2 by N1 under root. This is the fractional change. Delta is the fractional difference between refractive indices of core and cladding, known as fractional refractive index change. Okay, so delta is equals to N1 minus N2 by N1 itself. Okay, not the 2, along with the 2. So, root over the total Na is equals to N1 into root over 2 delta. Okay, next. So, we came through, we have up to now we have learned about what is an optical fiber, the structure of an optical fiber, how the light enters through the optical fiber, that is the principle of optical fiber, and also acceptance angle and numerical aperture. Let us now consider what are the advantages of optical fibers, why optical fibers are used. So, the fiber optic cables have high information carrying capacity. Why? Because they are very thin and also they are very flexible also. These cables have much greater bandwidth than metallic cables. The optical fibers are less susceptible to signal degradation than the copper wires. So, signal degradation means whenever the signal goes from one end of the cable to the another end of the cable, then the signal need to go without interruption. Okay, if it is interrupted, that is known as signal degradation. The optical fibers are less Data can be transmitted digitally. Lower power transmitter can be used instead of high voltage electrical transmitter used for copper wires. Light signals from one fiber does not interfere with the other fibers in the same cable, unlike electrical signals in the copper wires. So, whichever the data sent through one optical fiber, the data will not be matched with other data or will not interfere with the other data of the other cable. Okay, no hazards of short circuit as in the case of metallic cables. They can be used safely even in explosive environments. They have high signal security, and also fiber optic cable is lightweight, small size and cheap. Okay, this is the introduction of optical fibers. Thank you.